Okay, folks, in this video, we are going to talk about the rock cycle. You've seen these pictures before, and if you remember back to when you've seen these pictures, you remember put them here to represent the three different types of rocks that exist at Earth's surface. The rock cycle describes how we interconvert those types by the various Earth processes that shape and create each of these different types of rocks. So we've got igneous rocks, sedimentary rocks, in the process of formation down here anyway. These aren't actually rocks yet because they're not one solid rock, and we'll talk about the definition of rock in this lecture. And metamorphic rocks. There are processes that change each of these into each of the other ones. And we'll talk about those processes today in this lecture. And we'll also talk about the definitions of these, what makes something a rock, and what makes something a mineral, minerals being the constituent pieces of most rocks. So in this lecture, we're going to have just two sub-lectures. First, we're going to talk about the definition of rock and the definition of mineral, as I said. You're not going to want to confuse these two. You're not going to ever want to say that something that is a mineral is a rock or vice versa, because they have very specific definitions that I'm going to hold you to knowing. So you're going to want to know these definitions. They're going to show up over and over again in this course. They're pretty fundamental. In the second part, then we'll actually start talking about the rock cycle in those three classes. And then we're going to spend several of the next lectures talking about each of those classes in more detail. So the rock cycle itself involves, as I said, the transitioning between these three different types of rocks. For a quick definition here, remember that igneous rocks form from molten material. They form from a melt. When we say melt, that's magma or lava. Sedimentary rocks are going to form from pieces of other rocks broken down at Earth's surface. And metamorphic rocks form from heat and pressure without melting. Once you start to melt, what happens? You must be forming an igneous rock. And here we've got the cycle diagrammed out for the first time. So we'll take a look at this here. We've got, remember, sedimentary, igneous, and metamorphic rock. And you will want to know the processes that interconvert each one into each other one. You'll notice here that we have igneous rock becoming metamorphic rock as a result of heat and pressure. It's the same thing that transforms sedimentary rocks into metamorphic rocks. Same heat and pressure, when applied to these rocks, sedimentary or igneous, is going to turn them into a metamorphic rock if enough heat and pressure is applied. So conversely, when we talk about igneous rocks forming from melt, first we've got to take whatever rock it is and melt it. You'll see we really only have two ways of doing this. We could convert it from igneous rock, we could melt that. We could melt a metamorphic rock. Why can't we melt a sedimentary rock directly? Well, we sort of could, except that if we started to apply heat to this rock to start to melt it, it was probably going to go by way of a metamorphic rock first. So that's the only reason we don't have an arrow in there. I'm not going to ask you any question about that in this course, but you should know that igneous rocks are always going to start from magma, which is that liquid rock material, and we call it magma if it's underground. Once we cool that material, then we're going to form that igneous rock. The last limb over here is going to be the sedimentary rocks then. You can take any of these, igneous, metamorphic, or sedimentary, and you weather them, weathering being the breakdown of rocks, and then you erode them. You move them away from their original location to a new location. And after you've done this, you're left with non-cohesive, not put together, bits of old rocks. Those are called sediments. And if you will stick those sediments together into one solid body through a process called lithification that consists of these different sub-processes, you will change from a sediment into a sedimentary rock. So if you want to take a look at what some of these look like just as a first pass and where it is that they form at Earth's surface, igneous rock, they form from a cooling melt. And because they form by crystallization, that's the solidification, much like you would crystallize ice from water, they end up being what we call crystalline rocks. Depending on how big those crystals are, some of them you can see with your naked eye, like you can see these are individual sort of geometrically shaped crystal grains here. They're not all these round little pieces, but they look like some of them at least have edges that connect to one another. And some of them are dark, some of them are light. This is what a crystalline rock looks like. In some rocks, you can see those with your naked eye. In some rocks, the crystals are too small and you could only see them with the microscope. But if you had that microscope, you could again see that their texture is going to look very similar to this. They're going to be made of individual crystals. Let's take a look at where those form, right? Some of them form deep underground in a magma chamber that's cooling off, and some of them might form in the limbs of a volcano here at Earth's surface. So remember that this stuff is called magma. Once it comes out onto Earth's surface, it's called lava. And forming underground or at Earth's surface, that's going to have important implications that we'll talk about eventually. So where are the sedimentary rocks forming? Sedimentary rocks must be exposed at the surface to form, and they're going to weather, they're going to break down. Maybe they break down off of the flank of this volcano, rain hits them and they start to break apart, and then they start to move down slope, they erode, and they might then get deposited on this beachfront here, where they get reworked, and over time, they get buried, which allows them to lithify. We'll talk about how that works later. They might look something like this. Sedimentary rocks often have layering to them, depending on how they were deposited. And they tend to be deposited in layers because gravity is going to make these things settle out. The sediments will settle out into these layers as they form because they're forming at Earth's surface. So it's not often that you see any sort of layering in the igneous rocks, although it can happen. In contrast, the sedimentary rocks are often going to have layering. Some metamorphic rocks will also have layering, so layering doesn't necessarily mean sedimentary rocks. Let's look at where those can form. So metamorphic rocks, right, they're either next to something hot like magma, maybe they're near this magma body that is intruded underground, or they could just be buried very deeply and have no association with igneous processes. At any rate, high temperatures and high pressures in the deep crust and upper mantle are going to transform other rocks, igneous rocks or other sedimentary rocks, over time by a process called recrystallization, and that's in the solid state, never melts. And because these processes form new minerals, we call it a metamorphic rock. Some of those can end up looking crystalline, because, right, it's a similar process. This is recrystallization, where you're taking old minerals and turning them into new ones. So some of these are crystalline rocks as well. But some of them look a little bit more like sedimentary rocks because they're only a little bit transformed. We'll talk about all those as we go forward. So we've been using the term rocks a lot so far, but let's go back and define what they are and talk a little bit about how we're going to refer to them in this course. So these are the parts of the definition as underlined here that you're going to want to remember. Rocks have to be naturally occurring. If humans make something, we don't consider it a rock. Has to be solid. So one solid body. If it's a bunch of pieces scattered like sand on a beach, we don't call it a rock yet, because that's a pile of sediments. It's not one solid body of rock. And in most cases, the rocks have to be made of minerals. Aggregates, meaning collections of various pieces of minerals. But remember that they're solid. So if we were to take that pile of sand that we talked about, and we were to lithify it by burying it, by sticking all those grains together, you get what is called a sandstone. And that is now a rock because it is a solid aggregate of mineral. It occurs naturally. Once in a while, some rocks are made of non-mineral solid matter. Either they're non-mineral, well, we'll talk about the definition of mineral soon, but some of these might be because they're organic, they're not inorganic. That's a key part of the definition of a mineral. Some of them because they're not quite crystalline, because they're not, we'll talk about that as well, but if they're amorphous solids, we won't call them minerals, but they might still end up being called rocks. So 3 parts: naturally occurring, solid aggregates of usually minerals, but sometimes other non-mineral solid matter. 1, 2, 3. We identify them at a smaller level than talking about whether they're just igneous, sedimentary, or metamorphic by determining 2 variables. These are variables that are going to come up over and over again. We're going to learn lots of vocabulary related to each of these, but their identity is determined by these 2 variables: their texture and their composition. You'll look at this in lab as well, but texture tends to refer to things like how big the pieces are in the solid rock itself, how those pieces are oriented, and their relationship to one another. Things like that tend to be texture. Composition, in contrast, is what the material is made of. So it's chemical identity. And that could be the minerals themselves, often it is. Or we might talk about the chemical elements that make up those minerals. So just to repeat for you, here are your 3 parts of your definition of a rock. Go over these over and over again: naturally occurring, solid, aggregates of mineral, and sometimes non-minerals. So here's an example of a rock that we're going to see a lot: granite. You can tell that it's crystalline. You can see the crystals in there. This one is igneous. And it has several minerals that make it up. You can see very clear to grayish grains that tend to be irregularly shaped in this rock. Those are probably quartz. You see some that tend to be a little more rectangular in shape in general, at least overall. It's hard to tell in some of these, not always rectangles. But they tend to be a little more regularly shaped than like these weird quartz crystals are, right? Those are feldspars. We'll talk about some of those. And then there are also dark minerals, some of which are going to be hornblende in here. So these are some examples of different minerals. And then you also have rocks that are made of non-minerals. Turns out coal, different types of coal, are actually formed from organic plant matter, bits of leaves and whatnot, sticks that get stuck together and changed over time into coal without decomposing. In some cases, in rocks, you can see the grains. These you can see with your naked eye in granite, but in some you can't without a microscope. So here's an example of what basalt looks like. You really can't tell what's going on just by looking at the surface, especially a weathered surface that's started to break down. It kind of looks like the surface is rusting a little bit. If you look at it under a microscope, though, you'll start to see those crystals, some rectangular ones. Again, in this rock, these light rectangular crystals are probably feldspars. And the dark ones, they're probably not hornblende in here, but they're other dark minerals. Okay, so we know what a rock is. What about a mineral? Mineral, the definition is going to be a little more complicated. There are 5 parts to this that you're going to want to know. And we are going to do, our first major lab is on minerals and learning to identify some of those minerals. Minerals are naturally occurring. They're solid. So far, it doesn't sound too different from a rock. Crystalline substance. This means that the atoms are ordered in a 3-dimensional shape that is consistent across all samples of a particular mineral. And we'll look at sort of a microscopic level what some of these atomic ordering patterns look like so you can wrap your head around what that means. They're crystalline. those atoms have a distinct 3D pattern to them. We're going to say minerals are inorganic. They're not made of complex organic compounds, complex carbon-based compounds, we'll say. The thing that distinguishes organic from inorganic is the fact that these carbon-based compounds that make up a lot of what makes up living things like you and I, are that carbon can form really complex individual molecules with really complicated bonding patterns. Most of the time, minerals, things that are formed by abiotic processes, are going to have much simpler, relatively speaking, bonding patterns. They're not going to be, they're not going to make molecules for the most part, which are sort of separate entities that might only, you know, they might have had shapes that look something like this, where we can draw the bonds between each of these atoms. You might remember some of, you know, structures like this from chemistry class. We're going to try to not talk about that too much in here, but we will have to talk about the chemical structure of some of these compounds. At any rate, inorganic means not made of complex carbon-based compounds. Naturally occurring, solid, crystalline, inorganic, and minerals have a specific chemical composition. That's the fifth one. We can define pretty precisely the elements that make up a given mineral. So how does this differ from a rock, right? A rock can be made of multiple crystals, or sometimes they don't have to be crystals at all that make it up. But it's not one pattern. If we go back and look at something like granite, right? We can tell that there's multiple crystals in here, and each of these is going to have a different order to them, and they're not organized in any particular pattern. You know, feldspars are sort of scattered throughout this rock, and the hornblends are scattered throughout this rock too. It's not like you have, you know, individual crystal of quartz, individual crystal of hornblende in a particular order, right? That's because the minerals that make up this granite can sort of be ordered chaotically, whereas in a mineral, the atoms that make it up are going to have to be ordered. Rocks can be organic, minerals really cannot be organic. And specific chemical composition, we'll talk a little bit more about why rocks don't have a specific chemical composition, that things fall into much wider ranges, whereas in a mineral, you can pretty definitively say what atoms are going to be in that, what elements are going to be in that. So walk through some examples. Minerals are naturally occurring. This is part of our definition. Diamonds, we find naturally. Diamonds are networks of carbon that are connected in a relatively simple pattern. It's just these tetrahedra of carbon connected to four others, and each of these makes a tetrahedron. Tetrahedron being four sides. We'll talk more about that soon. Tetrahedra are important patterns that end up in crystal structures. But at any rate, we know we can find these diamonds naturally. They come from places that we can mine. So diamonds are going to be minerals. They're naturally occurring. Whereas we make this substance called cubic zirconia, we've never found this naturally occurring, this combination of zircon and oxygen. Because we never find it naturally, and we only ever make it to sort of substitute for diamonds, to make cheap diamond substitutes, this is not a mineral because it's man-made. Minerals are solid. So the material in here, this isn't one crystal of mineral, but this rock over here is made of those individual mineral crystals. If you looked more closely at it, you would see that this stuff is likely a mineral, whereas the water down here is not mineralic. Now, if you were to freeze this water into ice, ice is a mineral because now it's solid. You can melt minerals and then they become not minerals, right? So magma, because we talked about magma as being this liquid rock, magma is not made of minerals. So solid is an important part of that definition. Minerals are crystalline. So crystalline, remember we said, means the atoms are ordered. A pattern like this one down here, the atoms are very well ordered. This is just a 2D representation of a 3D shape here. You can see it's got atoms that are repeating at a very definite spacing in a particular direction. And then these atoms down here are repeating the same way, they're offset. But you can just look at this and tell that there's a repeated pattern, and you can say exactly where the next atoms are going to be if you were to extend this pattern out some more, right? Because we look at this and we say, oh, I can definitely see an order to this. This means that the atoms are ordered. This means that it is crystalline. As long as we meet all the other definition pieces of a mineral, this could be a mineral. Up top, though, this arrangement here, all of these atoms are disordered. You can't guess exactly where the next atom is going to be. Is there going to be one here or here? You're not really sure. Because these don't fall in any particular pattern, they're very chaotically scattered here. This is an amorphous substance, and it is non-crystalline, so it's not a mineral. Write that word just so you see it again. Amorphous, non-crystalline, disordered. Here's a more precise example with a real mineral. Biotite, mica, is this mineral down here. It's got these sort of flaky layers here. It's hard to tell in this picture, but if you took a piece of this, it would look like these are sort of thin, plasticky looking sheets that you can peel off from one another. Biotite is a naturally occurring mineral. Of course, it's naturally occurring. That's part of the definition. And it is crystalline. If you look at the atoms that make it up, here's what the pattern actually looks like. So we've got some silicon atoms in here and some oxygen atoms and other stuff mixed in here as well. But just looking at this, you can tell that there's an order to it. There's a layer of these silicon and oxygen atoms arranged in a certain way. And there's a layer of these other atoms, which are other things that we'll talk about. There's some iron and magnesium in there, maybe just a touch of aluminum. And there's more silicon and oxygen up there. There's a layer of purple atoms that are potassium right there. But these layers repeat over and over again. Each of these is something like, on the order of 10 to the minus 10th meters across. So in a sample that were this big, you'd have billions and billions of layers. But if you look at any one of those layers, it's going to look very similar to what we've diagrammed here. Very ordered pattern of atoms. And if you turn it and look at its side, you'll see that these atoms are actually arranged in this sort of 2D network here that we call a sheet structure. And it's behind why the mineral itself actually forms sheets. So a lot about the crystalline nature, the pattern of how the atoms arrange themselves is going to be behind a lot of the properties of these minerals. So that's part of why it's important that minerals be crystalline, because it allows them to have very consistent properties. Some examples that you'll see later on, these glasses. Obsidian is a glass, pumice is made of tiny little glass shards stuck together, and ash, this dust. None of these are minerals because they all have an amorphous structure that looks a lot like this. So some examples of a structure like this would be obsidian, the pieces in pumice, and the sediment, the little bits anyway, that make up ash. As a result, we don't call these minerals, but at least these two count as rocks because they're solid and natural. And they're aggregates of amorphous, not inorganic matter. Now, why is the ash also not a rock? Because the ash is just this pile of pieces, because it hasn't been lithified, turned into one unit. That's another reason the ash would not be considered a mineral. Last piece, minerals are inorganic. Amber It's solid. It has a relatively consistent composition, but it's made of very complex organic compounds with weird structures where we can draw them and might have nitrogen groups or oxygen coming off of it, and those are linked to other shapes. At any rate, amber, because of that, and it comes, it's like solidified tree sap, really. Because it comes from organic compounds, it's not a mineral. Even though it's solid, it might have a very defined composition. And in some cases, it might even be a crystalline where these compounds arrange themselves in a particular pattern, but it's still not a mineral because it's organic. It's made of complex carbon compounds. Galena has the elements lead and sulfur in it. It's lead sulfide. There's no carbon in there. And these just stack themselves into a cubic shape. We'll see that later. They stack themselves that way. Boo, boo. Perfect cube. Yeah, looks great. Nice art. Galena, it's inorganic, only lead and sulfur, so we can call that a mineral because it meets all the other parts of the definition too. Oh, sorry. Inorganic, that was actually 4. 5th piece here. Specific chemical compositions. Something like quartz, and here's what a crystal of quartz might look like. Has these very ordered faces. We look at this and we tell it's probably crystalline because it stacks itself into such regular shapes with a regular geometric pattern to it. So that's part of the definition of mineral. But the other thing about quartz is that it's made of 1 atom of silicon for every 2 atoms of oxygen. You're going to see quartz over and over again. So it's good to get this formula into your head. 1 atom of silicon. There's no number here, so it's just implied 1. But we could write that in if we wanted to, for every 2 atoms of oxygen. And if you really want, you can go through the structure and count up that seems to be the case here. Each silicon has 4 oxygens attached to it. Each oxygen has 2 silicons attached to it. Count it all up and you'll see that there's 1 silicon for every 2 oxygens. Because it's got a very specific chemical composition, and we're not saying, oh, the silicon can be aluminum, or it can be iron, or it can be magnesium, and the oxygen, maybe that could be sulfur. Because that's not the case, this has a specific chemical composition, and we can call it a mineral. So, quick thought question. Think to yourself, based on these definitions, which of these are minerals? I'm not asking about rocks, I'm asking about minerals. And how do you know? We've seen a couple of these already. So take a moment, think to yourself, come up with a guess for each of these. Let's see if you were right about this. We mentioned coal once already. It's not. Why is that? Well, it can be a solid. It's definitely naturally occurring. But as we said, it's made of complex organic matter because it comes from plant matter. So it's organic. Not organic in the sense that your food is organic, right? It's organic in the sense that chemists or geologists talk about it. It's organic, made of complex carbon. It also turns out that it doesn't have a regular crystal structure because it's got all these weird, crazy, different compounds that make it up. So this is not. Granite, it's made of minerals, but it's not itself a mineral. Don't call granite a mineral. We look at it and we can see different bits. And the fact that this has so many different colors in it indicates to us that it's probably made of different pieces of things. These pieces of things, because they have different colors, probably have different compositions. So it doesn't have a defined chemical composition because its composition can vary depending on what part of the sample you're looking at. And it doesn't have a defined crystal structure because these minerals all have different structures, and putting them together in this sort of chaotic way, granite itself does not have a defined crystal structure because it's just minerals jammed together. Now, what about garnet? You haven't seen that before, so maybe you're not sure. But if we tick down the list, garnet, is it natural? Well, you can find garnets in rocks or countertops. It's natural. Looks solid. Is it organic? No, it's inorganic. You're gonna have to trust me on that one. It's a lot of aluminum, a lot of oxygen, some other metals. Does it have a crystal structure? It's not a sure sign, but the fact that it's got this regular pattern of flat faces all meeting one another, not a sure bet, but it's likely. So yes, it does have a crystal structure. If you zoomed in and looked at the atoms somehow, you would see that those atoms are arranged in a repeating geometric 3D pattern. And does it have a defined chemical composition? Well, looking at it, it looks like it's homogeneous. So we know that at least its chemical composition doesn't look like it changes across this one bit of garnet. And it turns out that it does have a defined chemical composition with some elemental substitutions, which means that we might say that one metal might substitute for another one sometimes, but it's within a very narrow range of substitutions, and that's allowed when we're talking about minerals. So I'll point that out now. It doesn't mean that the minerals always have exactly 100% the same composition, but that we can very easily define the range in which the compositions can change for these things. So garnet is a mineral. That one is, granite's not, coal is not. Now, which of these are rocks? Well, granite's a rock. It's solid piece and it's made of minerals that are all stuck together. Coal is as well. You can find solid, unified seams of coal. The only reason this is broken up into pieces is because we've mined it and broken it up already.